All right, today we are jumping into a really core concept in precalculus, transforming the graphs of functions. We're going to see how just one little number can stretch, squash, and totally change how a graph looks. So to get us started, I have a question for you, and it's probably not one you were expecting in a math explainer. What on earth does all this have to do with your favorite song? I know, they seem like two completely different worlds, but believe me, they're connected by one simple, really powerful idea. And the answer is amplitude. You see, sound waves can be modeled by functions, something like a sine wave. So when you crank up the volume on your stereo, you're not changing the song itself, right? You're just changing its amplitude. You are literally increasing the A value in an equation like y equals A times the sine of x, which makes that sound wave taller. That is a vertical stretch in the real world. That real-world example is honestly the perfect way to get into the math behind it all. We're moving beyond those simple shifts, where the graph just slides around. Now we're talking about what's called a non-rigid transformation, where the actual shape of the graph is going to change. And this is all controlled by one main idea: vertical scaling. The concept is actually pretty straightforward. You just take the output of a function, the f of x part, and you multiply it by some constant, which we'll just call a. And that one single multiplication, y equals a times f of x, is what's going to control everything, whether the graph gets taller or shorter. So how does this a value actually work? Well, it just breaks down into two really simple cases. If the absolute value of a is bigger than 1, so think numbers like 2, 5, or even -3, you get a vertical stretch. The graph gets taller, and every point on it moves away from the x-axis. But if a is some fraction between 0 and 1, like a half or 0.2, you get a vertical compression. The graph gets shorter, like it's being squashed down towards the x-axis. And the rule for actually doing this to any point on the graph is super simple. For any coordinate, let's say x comma y, the new point just becomes x comma a times y. Now notice the x-coordinate? It's left completely alone. All the action, all the change happens vertically to the y-coordinate. That is so crucial to remember. Okay, theory is great and all, but seeing this in action is where it really clicks. So let's move on to some examples and see how this all works with a few common functions. Let's start with a basic parabola, f of x equals x squared. Now, if we want to graph g of x equals 2 times x squared, our a value is just 2. So we take our key points and we just multiply their y values by 2. The point 1, 1 becomes 1, 2. The point 2, 4 shoots all the way up to 2, 8. See? The graph just gets twice as tall, way faster. Now let's do the opposite, a compression, or, a squish. Take a look at the function h of x equals 0.5 times the absolute value of x. Here, our a is 0.5, which remember is between 0 and 1. So this means every single y value gets cut in half. The graph now rises half as fast, which makes it look visually wider or maybe flatter than the original. Okay, so what happens when we start combining these transformations? This is where people can get tripped up. For a function like k of x equals 3 times the square root of x minus 2, we've got both a stretch and a shift. Order of operations is everything. Remember PEMDAS? Multiplication comes before subtraction. So you must stretch the graph vertically by a factor of 3 first, and only after you've done that do you shift the whole thing down by 2. If you get that order wrong, you're going to end up with a completely different graph. I promise. And speaking of getting things wrong, let's talk about the most common mistakes people make with this stuff. Because honestly, knowing where the traps are is half the battle. Okay, here it is. The number one point of confusion. We just saw that when you compress a graph vertically, it makes it look wider, right? So, is a vertical compression actually the same thing as a horizontal stretch? What do you think? This is my absolute favorite analogy for this. It's best to think about the primary action. The function was squashed down vertically, but a side effect of squashing something like a ball of pizza dough is that it spreads out sideways. So while it might look wider, the transformation we actually performed was vertical. If you just focus on that x a times y rule, it keeps everything crystal clear. The other huge pitfall involves parentheses. If you see something like 3 times the quantity x squared plus 1, your first instinct might be to shift it up by 1 and then stretch the result by 3. But look closer. That shift is inside the multiplication. You have to distribute the 3 first. That gives you 3x squared plus 3. So what is this really? It's a vertical stretch by 3, followed by a vertical shift up by 3, a totally different result. So that was a lot of detail, I know. Let's just zoom out for a second and pull together the most important things that you absolutely need to remember from all this. Here are the essentials, kind of like your cheat sheet. It all boils down to that one rule: y equals a times f of x. If a is big, it's a stretch, it gets taller. If a is a small fraction, it's a compression, it gets shorter. And remember, you're only changing the y values, and you always do your stretching or compressing before you do any vertical shifting. If you can lock these points in, you've pretty much mastered this whole concept. And to leave you with one final thought to chew on, we've spent this entire time multiplying on the outside of the function, that a in a times f of x. And that clearly affects the graph's height, its vertical dimension. So, what do you think happens when we move that a to the inside of the function and we look at f of a times x? What does that transform? Think about it, and we'll see you next time.